to understand the mechanisms behind plate tectonics, the fancy phrase for describing how continents moved. First of all, we have to understand the structure of the Earth. If you could somehow drill down to the center, what would you find? This is all theoretical. The furthest we've drilled down is only about 5 kilometers, by the way. Barely anything. It's incredibly tough. The technology involved is incredibly tough. So this is theoretical, but we believe the Earth is made up of layers. I wrote here, complete the following from page 519. So if you have a textbook handy, someone at your table, crack it open to page 519. Open your textbook to page 519. And the reason I'm using your textbook is it has lovely color. 519.
Wow, good job.
519. And I've given my textbook away, so you folks are going to have to help me a little bit. So once you open to page 519, this letter right here, letter A, according to your diagram, what's it pointing to? What are we going to label that as? Okay. We talk about the Earth having an outer crust. Does it tell you any of the distances for the crust at all? Oh, let's add that in brackets. So how thick is it, Matt?
5 to 7 kilometers.
So basically, based on what I said about how far we've drilled, we really haven't gone past the Earth's outer crust. Okay? You guys have one textbook to look at somewhere there? Yeah, okay. Long as every table has one. And your picture is nice in color, yeah? Yeah, see, I, again, can't reproduce that. What's B? Okay, so we have, I'm going to guess if there's an upper mantle, it would be logical. There's probably a lower mantle. So upper mantle. So the crust is the outer, very, very hard part, what we think of as the ground. Upper mantle. Is there a thickness for the upper mantle? Sorry? 660 kilometers, is that what it says? Really? 606 or 6 to 6? Okay. And then we have, I'm going to guess, is C the lower mantle? That would just make sense to me if we have up. Okay. And how thick is that? Sorry, Matt? 2225? Basically, the mantle overall is right around 2,900, close to 3,000 kilometers thick. And it's barely liquid. When I say liquid, really it's a solid, but it's a solid that's sludgy enough that it can, because it's kind of like a very, very, it's like the thickest molasses you've ever seen in your life, even thicker than that, but it is technically liquid. It does flow, but not very fast. That's why the continents drift at the rate of about your fingernails growing. But it is, when I say liquid, just Allison, don't be thinking like, ooh, all bubbling and watery. I mean, it moves. Okay. So we have the crust, we have the upper and lower mantles. Then we run into, what do we call that thing there for part D? Outer core. You know what? If there's an outer core, what else could you probably guess that there must be? Is E the inner core? And then I think we can put some of these distances on the arrows, can't we? So what distance could I put right on that arrow? Is there one in the picture? What is it? This first arrow, 660? Right here? I'll do it in red, but I can do it bigger and brighter. What about the second group of arrows? That's the 2225. Now, I don't know if this will print for people that are away, but they can always download the original and look. And then how big is the outer core?
Not very much up. You have to shift everything down one.
I missed one? I don't know. That's what I'm asking.
No.
You know what? Maybe the crust is so thin that on this scale we just can't get it in there as a separate measurement, right? 2,270, and then we figure the core, the inner core, we figure is about what? What's the last one here? We can be we can be reasonably close. By the way, one of the reasons that we suspect that there is a solid core in the middle of the Earth has to do with earthquakes. And we'll talk about how that helped us. I mean, yes, they do damage, but they send powerful waves through the Earth, and we can read the echoes and use that to figure out what's going on down there. And the waves are bigger than that which we can create by hand, by machinery. So, each layer has a varying thickness, a varying state, solid, liquid, or gas, and composition. So it says, fill in the following table, beginning with the innermost layer in the order that you would find the layers from inside to outside. Okay, now we're going to start on the inside. On the inside. So we have inner core. Is that the first one, right? Inner core. How thick? Was it 1216 kilometers? What does it tell you in your textbook about the inner core? Does it tell you anything there? Solid, liquid? What was that, Sage?
No, because we thought.
It says to go from the inside to the outside. Oh, I didn't either. In my notes, I've got it backwards, and I just caught it now. So you're going to see me hesitate every so often as I'm reversing everything from my notes, too. What does it tell you that the inner core is? Okay, it's a solid. What's it made up of? I don't want to write that. Oh, I have chemical symbols. Fe. So you can remember the inner core is either Fe or knife, whichever is easier to remember. The only problem is if you think knife, you might be tempted to put potassium in front of it, so maybe that's not the way to remember it. Now then we have the outer core. What was the thickness for that one? That was in the 2000s. I remember that. Outer core, liquid. Ah. So here, it's hot enough that it's molten. Inside, it's technically hot enough that it should be molten, but it's under so much pressure that the atoms are so packed together that now they're going to behave like a solid. You learned in Science 8, gases are spread apart. Liquids, the atoms aren't quite as spread apart. Solids, the atoms are clumped together, and that's due to the pressure inside the Earth that you have that solid inner core. Then we have, was the lower mantle next? Yeah? Mantle is an old-fashioned word for a cloak or covering. Think of like a blanket for the Earth. What was the thickness of the lower mantle? What was the thickness? How many kilometers? 2225? Magnesium, I always get magnesium and manganese, Mg. You can write out the words, but for Pete's sakes, if I got abbreviations and we're getting towards the end of the year, so reviewing the chemical symbols is also a bonus. Femg. I'm not going to ask you specifically, by the way, for the thicknesses. I might ask you very roughly. In other words, you should know that the outer core and the lower mantle, they're in the 2000s. They're not 5 to 70. Okay, that's what I mean. Oh, and then we have the upper mantle. That was not as thick. How thick was that one? That was in the hundreds. 660? And this is what explains a lot. What state is it? Partly molten and partly not. Very, 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 very sludgy. And what that means is stuff sitting on top of it is going to move very slowly as it moves. Continental drift. What's it made up of? I think also the same stuff. Iron, magnesium, but I think also, do they say also just more generic rock or not? Like, is it molten magma and rock? Yeah. Molten rock. What you think of as lava on the Earth's surface, the upper mantle is technically magma, which is what you call lava below the Earth's surface, but far thicker and sludgier than the stuff that makes it to the top. So like people want to think, oh, it's just like oozing and churning. Yeah, over hundreds of years, over thousands of years. But it's not bubbling like the stuff you see on the top. Those are rare pockets of really hot that have escaped. Oh, and the last one was what I hate on the bread, crust. Raise your hand if your mom cuts off the crusts for you. I won't ask, never mind. And that was the really thin one, right, Matt? 5 to 70? Varies. And that's solid. It's made up of all sorts of rock. Silicate, but we'll just call it rock. The problem, Courtney, exists right there. You have a solid covering on a partly liquid inside. So, the surface of the Earth, the crust, is solid. Whew, good thing. In fact, the crust is made up of tectonic plates. If you look on the back of your green sheet, we've mapped them out. Those are the plates that make up the Earth's crust. The crust, the Earth's surface includes the crust and part of the uppermost mantle, and it ranges in thickness from about 65 to 100, give or take, different numbers from what I have there, because we're sometimes going to include some of the Earth's upper mantle, sometimes. Anyways, it's a little confusing. Don't freak out. Next, the next layer after the surface crust is here's our word of the day, Theno sphere. That's Thenosphere. It almost looks like asthenosphere, but it's not pronounced as then. It's asthenosphere. Sphere, round. This is the semi-liquid section, the part of the upper mantle that's semi-liquid, and it allows the plates to move around. So it's liquid, barely, but it has large temperature variations. There are parts of it that are nearly solid. There are parts of it that are really hot and really, really runny like lava that you see bubbling to the surface. Why are they liquid? Well, they have to because of heat. Where's the heat coming from? We think, I kid you not, that the heat, the melting, the liquid is caused by large pockets of radioactive elements like uranium, and as they decay, they give off heat. I don't know if you realize that the Earth down there is that radioactive. It is. This uneven heat distribution, where you have hot pockets and cold pockets, leads to, here's a word that you'll probably need to know, convection currents. What are convection currents? Well, you know this. Hotter material in the mantle will... What does hot air do? Hot rock does the same thing. It starts to bubble up, it starts to rise, and again, I'm moving my hands quite quickly. Again, think very slowly. But as it gets higher, as it gets further from the radioactive heat, it's going to cool. And when it cools, what? Drop back down, pulling other rock in its place. Do I want to say sink? How about sinking is a good word. Then it repeats. So I think in your notes I gave you two pictures. I gave you a cross section of the Earth's surface. So we have something on top that we call the lithosphere. Then below that is the asthenosphere, and both of those together make up the upper mantle. This is right from your textbook. And the continental crust is the surface parts on top. The oceanic crust is the parts where the ocean is on top. But then here's your convection currents. So here is a hot area. It bubbles up, it cools, it falls down. Right here, you would expect the Earth to be getting tugged apart. Very slowly. Compare that with right here, because it's moving this way and this way. There you would expect the Earth to be getting pushed together, and probably, what are my hands forming? Mountain range, probably. Oh, pulled apart, probably a rift valley. And, the next question then, Allison, is what if instead of moving apart, what if instead of coming together, what if they're moving side by side? We'll talk about that too, because that can also happen. We're looking at one part, it's three-dimensional in real life. So, as the plates move, they can interact in several ways. They can pull apart. We have a fancy word for that. It begins with the letter D, as in the name of a trendy movie that came out last year starring a girl as the heroine. We call this divergence. They can collide with either one sinking underneath the other. That usually gives you an ocean right there, because you've got it pulling one down a little bit and water fills it in. Or both pushing on each other, which would give you some kind of coastal mountain range. We call that, what's the opposite of divergence? Convergence. Or they can slide along each other. We call this a transform movement. Conveniently, they're on the bottom of your green sheet. In fact, on both sides. And you'll also see on both sides, there's the symbols for what they mean on the map. So do you have to memorize these words? You got to know what they mean. You have to memorize the symbols. You got to know what they mean and be able to find them on the map. Okay? The region where they interact, the region where they intersect, it's called the plate boundary. So can you, on the green sheet, look at the front part that has the BC coast? What are the tectonic plates that affect the BC coast? What's the huge one on the left side? So look at the front page. What's it called? Find the plate name. The Pacific Plate. Okay? Called the Pacific Plate because what ocean sits on top of it? The Pacific Ocean. And then there's a huge plate on the right-hand side. Which plate is that? North American Plate, called the North American Plate because it makes up North America. Oh, we also have a little small one. What's the little small plate there? By BC. Isn't it the Juan de Fuca? You guys looking at the right page, the BC one, right, the front page? So there's a Juan de Fuca. Could we also call it the Juan de Fuca Strait? So it's named after the explorer that found this area. And the fact that we have 3 intersecting plates, we get some earthquakes. We're going to get some earthquakes. We get some volcanoes. We're going to get some volcanoes. We get some coastal mountains, and we're going to get some coastal mountains. Mount Baker's a volcano. Pardon me? I have you look, follow it, there's a bunch. So, let's talk about how this can work. So the first type is a divergent boundary. Pull apart. How many of you have ever eaten a Mars bar before? Okay, it's one of my favorite chocolate bars. So I'd like you to imagine, because it's got a mushy center with some caramel, and then it's covered by a crust, it actually simulates the Earth pretty good. If you took a Mars bar and you pull it apart slowly, I think you would see, first of all, that cracks formed along the top, and then you'd probably see one big rift would form. I shouldn't be doing this last block because I'm starving. Anyways, okay, I was visualizing a Mars bar, and believe me, it was not going well. So, divergent boundaries, to diverge, you do need to know that to diverge means to pull apart. And this motion away from the ridge is called a ridge push. If it's happening in an ocean, underwater, we call this a spreading ridge. If it happens on land, which is more rare, but there is one big one that I know of, we call it a rift valley. So Kenya, the African country of Kenya, has a rift valley that runs right along the middle of it, a huge one. So, here's a lovely picture. Let's look at some of the terms here. Again, we have our crust, which is solid. Here's the upper mantle. That's the part that's kind of sludgy and that will move. Here's the lithosphere. So, we have convection currents bubbling up, magma bubbling up, and so it's pushing these apart. We call this a ridge push. Okay? You can have a convergent boundary, collision. How can I remember that convergent is a collision? I'll let you come up with your own way. We have oceanic plates, sit on top of the ocean, and continental plates. They don't sit on top of the continents, they make up the continents. Where they collide, we call this a subduction zone. The heavier oceanic plate goes underneath the lighter continental plate. Hey, wait a minute, Mr. Dueck. Wouldn't the continents be heavier because they have all the land on them? Let's be clear. The ocean plate has the same amount of land. It's just under the water. And it has the oceans on top, which adds way more mass. So without the oceans, they'd be almost identically massed because they have about the same amount of rock. But you throw an ocean on top, the oceanic plates, Allison, are way heavier. So what happens is they tend to go underneath the continental plate. So here we have a convergent zone. The oceanic plate is getting forced underneath the continental plate. We call this underline this phrase because you'll probably be asked this, a slab pull. A slab pull. Right here. And, Allison, once you have enough rock that's been forced underneath, it's got enough weight that not only is there pushing from here, it's going to start tugging it along because it wants to sink now because it's got so much mass. So not only do you have this oceanic plate being pushed because of that spread there, it's also getting tugged from the slab pull. Oh, here's your subduction zone. And this is why if you look off of the coasts of most continents, there's a sharp drop-off all of a sudden, a huge trench. That's where the continental shelf ended and the oceanic shelf is starting. The oceanic plate is starting. You get a trench. So far, so good? Okay. There's your convection currents explaining why there's magma bubbling up here, forcing these apart, slab pull. Let's fill in some more blanks. This leads to, well, this is what we're dealing with. Lots of earthquakes. Lots of volcanoes. Because you can imagine that if you take a Mars bar and you start to push it together from either end, come back, you're going to see some cracks appearing in the middle. That's spots where in real life magma could start to bubble up. There's weak spots. You might get a volcano. Not always, but you might. Okay. We have a volcanic belt along our coast. I should grab a green sheet since I gave it to you folks. I think they labeled a bunch of the volcanoes. Sage was saying, "Oh, I want some." We got a bunch.
No, but I want one that is a little rough.
You really don't. But I know what you, but like on one hand, it seems kind of cool. You really don't. Okay? So already starting in California, you can see there's the Cascade Mountain volcanoes. There's Mount St. Helens, Mount Baker, beautiful mountain. It's an inactive volcano, we think, right now. And then as you go north, and then it goes all the way across to Russia. In fact, we call this the Pacific Ring of Fire. It goes in a huge circle all the way through Russia. It goes down along the coast of Asia, down through Japan, also down our coast, down through South America. These are where plates are creating earthquakes and volcanoes. Hey, has Japan had a massive earthquake in the past few years? Now you know why. Has Chile had a massive earthquake in the past few years? It's on the coast of South America. Yes, it has. Are we due for one? We really are. And that's not to be doom and gloom. That is to say, you should at least, when the newspapers or when people start talking about earthquake safety, you should take it a little seriously. Don't freak about it, but it's worth having, for example, at each house, some kind of an earthquake bag. You want some water, enough to go for 3 or 4 days, because almost certainly if there's an earthquake, the first thing to go is going to be your water pipes. You're going to turn the taps, and either nothing's going to come out, or nothing you want to drink is going to come out. Everything else, you can survive for 3 or 4 days without food, or you can have some canned food, maybe a camp stove, and then you're good, because you can survive for 3 or 4 days without electricity. Water is the big one. Yeah.
I was looking at this thing online.
Yep.
It's about Yellowstone National Park.
Oh, yes.
There's not a bunch of people freaking out about it.
Oh, yes.
But like, it's not. It went around for like hundreds of thousands of years, is what I read.
We think.
But yes, I was looking at it. They showed a map of like the area that would be
Yep.
affected by it, and it's literally like 3/4 of the United States would just be
Yep.
dead. Like straight up
So
dead.
Yellowstone National Park has those cool geysers, those hot water springs. Those are all suggestions that there's some magma pressure down low. And when we crunch the numbers, first of all, we think Yellowstone had a huge, massive eruption several 100,000 years ago. And yeah, when we run the numbers, we've tried to trace it out, and it looks like it takes up about 2/3 of the U.S., and it's a ticking time bomb set to go.
No, it's right down
Now,
there.
not for several 100,000 years, but it would, I don't know, it would make Mount St. Helens look like a soap bubble bursting.
Yeah, no, it was crazy. They were talking about like, and they had like certain like how dangerous each zone was, and like the first like 100 kilometers around.
Oh, yeah.
It's like, okay, so you're dead. Like you're gonna be
Not just dead, probably we would find nothing of you.
Yeah, yeah.
You'll
Like,
get vaporized.
this whole area is just gonna be like ash, and then they're like, okay, then the next like 100
Which, honestly, not to be morbid, they're the lucky ones. Because that would probably change the entire climate of the Earth. It would throw enough ash and dust into the sky. Probably daylight would be much dimmer for about 15 or 20 years, which would basically mean most crops would not be able to grow, and humanity would dwindle and dwindle. Probably some core of humanity would survive, but it'd be ugly. It would be like an apocalyptic movie.
Yeah, well, they're just talking about how like southern Canada and the
Preview of coming attractions. Sorry.
They said that like southern Canada and the whole of the United States
Yeah.
would just be covered in ash, like nobody would be able
Yeah,
to survive.
and not to scare you, Alex, we have hot springs here as well. We're not on as big a one, but we are also on a fault.
Would our earthquake be as big as the one like that was in Japan?
Pardon me?
Would it be as big?
Probably bigger.
Smaller.
Now, what's this a symbol for? Can you look on your green sheet? Look up. Because this is how they're going to, on your provincial, they're almost certainly going to give you some kind of a geology diagram. So what's this a symbol for? How can, now, that's a symbol, convergent, look up. Convergent means coming together. Can you see why they picked that as a symbol? Okay? That's how I remember it. You don't need to, but just so I know which one it is. So here's a convergent boundary. So where it's converging here, you have the upper mantle getting forced. Here's slab pull. And because this is cracking, you may have some volcanoes. And the other issue then, Courtney, is this. You asked how big is our earthquake? See, here's what happens. As this goes, now this is solid rock. Watch this hand here. As it goes, there's pressure building, and all of a sudden, that's the earthquake. That's what happened to the Japan quake. Okay? There's a great, I watched Nova, which is a science special on PBS, and in the Japan quake, they did a great special afterwards looking at it, talking about what all happened. There was a coastal town, because Japan takes earthquakes very seriously. And this coastal town had built a 30-foot high dam to prepare for a tsunami, because they had run the numbers, and the highest tsunami they could get was 28 feet. So they built a 30-foot dam. Yet the water after the earthquake went over the dam. Not because the tsunami was more than 30 feet high. It was still only 28 high. That earthquake was so strong, Japan dropped 10 feet. Yeah! It's crazy. And sorry, when they ran the numbers tight, they didn't expect their entire country to sink into the earth. No one thought of that, which is kind of understandable. It was that big. So here's the coast mountains of BC. This is what we're dealing with. Now, by the way, here's the flip side. There's a reason why we have such gorgeous mountains here. I mean, I love living here. There's a reason why we got coast right here. I mean, this is a beautiful place to live by the ocean. But understand, on the global scale, you win some, you lose some. There's a second possibility. Turn the page, or next page over. Instead of having a continental and an oceanic, because the oceanic is heavier, it'll dive down, you could have two oceanic plates. Well, one of them might still be heavier, so again, like before, the heavier plate will slide under the lighter plate. Except this time, you don't have anything necessarily above the ocean to begin with, but what you might get is an island chain, because you might get volcanic activity and the lava bubbles up. When it hits the ocean, it turns solid, more bubbling up, and this gives you an island chain like Japan and Indonesia, two more places where there are lots of earthquakes. Oh, Indonesia, that's where the tsunami in 2005 was that killed over 250,000 people. You're all going to die. The death rate's still 1-to-1. Tyra, you're going to die someday. Figure it out. Sorry, but, right? What you're asking is, are we going to die due to some earthquake? Not if you take some basic preparations. Pardon me? Well, I'm going to pause the video for a second. My kids are all getting worried. So, Japan, Indonesia, those are island chains. Those are different from Hawaii. Now, Hawaii is also an island chain, but it was not formed where two plates are meeting. If you go look on a global map, there is not a plate boundary where Hawaii is. But Japan is right on a plate boundary. Indonesia is right on a plate boundary. It's on an ocean-ocean boundary. Or, another good example are the Aleutian Islands of Alaska. That's the islands up there on the map of BC. So, if you look at your green sheet, right? All these islands here, there are two. The Pacific plate is moving this way, and there's another plate moving here. One of them is going underneath the other one. It's causing cracks in the Earth's crust. Magma is making it through the cracks. When magma hits land, we call it lava. It solidifies, and over the decades, over the centuries, over the millennium, over the eons, you get islands. I mean, the positive is it's free real estate. The negative is, yeah, maybe 300 years from now, we might be Port Meadows. What else? Oceanic plates. Hey, you can have two continental plates pushing towards each other. The edges fold and crumple. You are going to fill in this blank on your own. Forming. Where is the tallest mountain range on Earth? That's two continental plates just running into each other. Understand that's different from Mount Baker. which is formed by volcanic activity. Allison, this is for homework as well. Can you grab this on your way out? That's different from some of the coastal mountains, but there you go. Oh, and as you just saw, Nepal recently had an earthquake as well. The Himalayas are still getting a few centimeters taller every year because those plates are still moving towards each other. Double check on the back page of the green sheet. Are there two plates roughly where the Himalayas are? I don't know where the Himalayas are. I'll show you. So, well, mine is sideways, but kind of. I think they're kind of in here-ish area, right? Yep.
Is it possible, like, so, is it more likely that, like, plates would mesh together, or that eventually plates will just keep breaking apart until we just have a bunch of little plates?
Generally, we find because one of them is heavier, it's going to get forced underneath, and as it gets forced underneath, when it gets lower and lower, where the Earth is hotter and hotter, that rock remelts, and the whole process starts again. In fact, we think that's part of the Earth's renewal system. We also think that's part of the carbon cycle, so we'll get into greenhouse and all that stuff in the next unit. We'll start looking at biology and biomes. We'll look at the carbon cycle. But we believe volcanoes are part of the natural re-emission of certain gases, but also then the continental drift and the oceanic plates, because a lot of it settles into the oceans, take it back down again into the Earth. It's really like almost a big recycling system. It's really kind of cool. But we're wrecking it as humans. Sorry. Plate tectonics explained, a little video. I showed it to you last class. I'll show it to you again later on because it really does explain things well. But it's not my fault. No. Earthquake faults. So, types of faults. We have what are called transform faults. Transform, that's where the plates are sliding across or beside each other. They're not coming towards each other. They're not going away from each other. They're sliding by each other. And if you want to know what can happen, if you want to put your hands like this and press them against each other really, really hard, and keep pressing harder and harder and harder and harder and harder and harder and harder, and slowly pull your hands apart as you're pressing harder and harder and harder and harder and harder. I was kind of hoping somebody would slap themselves in the face. But what happens is pressure builds up, builds up, builds up, builds up, builds up, builds up, and then suddenly the Earth realigns. What do we call it? Earthquake. Okay? Those are the earthquakes that California gets. That's probably the type of earthquake that we'll get, a transform fault earthquake. San Andreas Fault. You can actually see it from the sky. You can see a noticeable crack running along the coast in satellites. It's very obvious. I know which picture I need to show you. So what we have then in transform faults, as you found with your hands, because a bunch of you almost slapped yourself in the face, the energy builds up, builds up, builds up as the plate moves, but the boundary itself doesn't, and then it releases all at once, and you have an earthquake. What's the symbol for a transform fault or a transform boundary? Hey, this is a good symbol. It does look like two things moving in opposite directions along a shared boundary. Okay. So, do you need to know these symbols? They're on your green sheet. You need to know, Rachel, what they mean. They're at the bottom. Well, there's a legend bottom left on the front page and on the very, very bottom on the back page as well, and they tell you which are mountains and which are volcanoes. Part 2. A little more. By the way, all I want to do is finish this page here because for some reason I stopped at a weird location in the last section. So, some more terminology. You'll see some of these words on your test. Lithosphere. This seems to be a word they like to ask on the provincial. This is the layer of the Earth made up of the crust and the uppermost mantle. So under your vocabulary, that's one. Below the lithosphere is the as-then-o sphere. Blank pull. When the edges of a tectonic plate subducts it deep into the mantle, it pulls the rest of the plate. What did we call that? I showed it to you about 20 minutes ago. Do you remember what it was in the diagram? Starts with an S. Slab pull. Okay? That's a word that shows up on the provincial fairly often. So what that does then, there's actually two forces causing a plate to move. It's getting pushed from behind, but when that slab starts sinking into the earth and melting, it's got enough mass that it's going to tug it with it as well. So along with convection currents and ridge push, slab pull also helps keep plate tectonics in motion. See page 522 for a lovely color photo. When an oceanic plate collides with a continental plate, the oceanic plate slides. And again, this is counterintuitive because people want to say, wasn't the water lighter? No, no, no. The oceanic plate has as much land as the continental plate, but the oceanic plate also has an ocean on top of the land. It's heavier. Trust me. So it's going to slide under. A deep underwater valley, and this is the word that I didn't include in the last notes, but it was in the picture, called a trench. And then the last thing we're going to fill in, the map symbols for the three types of plate interactions. What's this one from your green sheet? Divergent. What's this one? Convergent. Forms mountains. And this one is transform. Now, most kids know what the word diverge and converge mean. Transform. How can I remember that that's two plates sliding side by side? Look at the symbol. Look at the symbol. I kind of like that. Out of the three of them, that symbol to me makes the most sense. Oh, they're sliding in opposite directions. The convergent one makes pretty good sense to me. The divergent one, but whatever, it looks different, and that's good. So what's your homework? I have two things, and you can get the rest of class. First of all, from page 523, see if you can answer these questions, and you can answer them right in your notes. Now, you don't need to actually use page 523. You can also use, I think it's all on the green sheet. I think 523, somebody got 523 open? Can you open to page 523, please? Is it the same as the green sheet that I just gave you?
Yeah.
Okay, or you can use page 523 or the green sheet. Find two plates that share a convergent. Find two more plates that share another convergent. Find two plates that share a divergent. This one's tougher. Find two different answer that. So finish this page, and then I have a one-page little handout for you here. Pause the video while I'm handing stuff out, Mr. D.